So far in this course, we've used molecular orbital theory to talk about the chemistry of diatomic molecules, molecules containing two atoms. We looked first at homonuclear diatomic molecules, in which both atoms were the same, and then at heteronuclear diatomic molecules, in which the two atoms were different elements. In this video, we're going to start talking about larger molecules, polyatomic molecules. And the rules for polyatomic molecules aren't any different than the rules for the diatomics. We are still going to be combining atomic orbitals to make molecular orbitals, and we're still going to be preserving the number of orbitals that we have in our molecule from the picture for the individual atoms to the picture for the molecule as a whole. We are still going to be separating those orbitals into the ones that are sigma symmetric versus the ones that are pi symmetric. And we are still going to be restricting ourselves to combining atomic orbitals that are close enough in energy, which we're using 1 Rydberg as an approximate cutoff. And the first example that we're going to look at is beryllium hydride, quite simply because it's the simplest polyatomic molecule that exists. We add a third atom, but 2 of our atoms are still hydrogen, and it's linear. You don't get any simpler than that. So, beryllium has an electron configuration of 1s2, 2s2, meaning that it's going to be bringing 2 valence electrons and that its valence shell is the n equals 2. Hydrogen has an electron configuration of 1s1, but there are 2 of them, and so that means that they each bring 1 electron for a total of 2 electrons, which gives us 4 electrons with which to assemble our molecule, draw a Lewis diagram for 3 atoms and 4 electrons. There's only one way to do it. We put the beryllium in the middle, and we make a single bond to each hydrogen atom. And it is very important to note that this is a linear molecule. As soon as we get past the diatomics, you have to draw the Lewis diagram first, and you have to use VSEPR to figure out the geometry of the atoms, because you can't assign sigma and pi until after you know the shape of the molecule. And so you can see that we've been given the energies of all of the atomic orbitals for both beryllium and hydrogen, including the 1s on the beryllium, but you can see that the 1s on the beryllium has an energy of -9 Rydberg. The closest thing to that is the 1s on the hydrogen at -1 Rydberg. Those are 8 Rydbergs apart from each other. That's not even close to our cutoff of 1 Rydberg. And so these guys here are core electrons. They provide some shielding, but we're not going to worry about them in our molecular orbital diagram because we're drawing valence molecular orbital diagrams. So you're there, but we're not using you in our diagram. Something else you may notice is that we have been provided the energy with both the 2s and the 2p on beryllium, and yet there aren't any electrons in the 2p orbitals in a beryllium atom by itself. So why is the 2p there? Well, the 2p is there because the 2p is very close in energy to the 2s. That's a difference of 3/4 of a Rydberg. So that 2p atomic orbital, despite the fact that it didn't come in with electrons in it, is still something that we need to factor into our molecular orbital diagram. And as it turns out, we can't actually get the correct picture for the molecular orbitals of beryllium hydride without the 2p orbitals. So it's very important that as soon as we identify that the valence shell for an element is the n equals 2, that we factor in both the 2s and the 2p. So we have been asked to identify which valence atomic orbitals will combine to make sigma MOs, which will combine to make pi MOs, and which will have nothing to combine with. Well, in order to do that, we're going to have to start off by sorting them into sigma and pi, as we have done in every other example of molecular orbital theory. Usually easiest to start off with the s orbitals. We have 2 hydrogen atoms, each of which has a 1s orbital on it, or each of which brings a 1s orbital to the molecule. Those 1s orbitals do not have nodes passing through all 3 atoms, so they are sigma symmetric. So we have 2 times a 1s orbital on the hydrogen. That takes care of that. Our beryllium atom also has a valence s orbital, which looks like this. Also sigma symmetric, no node passing through the whole plane of the molecule. So we have the 2s orbital on the beryllium, also sigma symmetric. Now, in the 2p category, we of course have 3 2p orbitals, each pointing in a different direction. If we look at the 2p orbital pointing left and right on the beryllium, we can see that that is also sigma symmetric. It has a node, it passes through the beryllium, it doesn't touch either hydrogen atom. So the node does not pass through the whole plane of the molecule, and therefore that 2p orbital, the one that points left and right on the beryllium, is sigma symmetric. We also have a p orbital pointing up and down. That one has a node that passes through all 3 atoms. That node passes through the plane of the molecule, so that p orbital is pi symmetric. So that is the up and down p orbital that is pi symmetric. Similarly, we have the p orbital that points forwards and backwards. It has a nodal plane. That nodal plane is the page I'm drawing on, so I can't really draw it for you, but if you picture it, it does indeed cut through all 3 atoms, and so that is the 2p on beryllium that points forward and backwards. So now that we've gone ahead and sorted all of our atomic orbitals into sigma symmetric and pi symmetric, we can go ahead and assign x, y, and z to our 2p orbitals. We have 2 directions of 2p orbitals that are pi symmetric, so those will therefore be x and y, whichever way around you want to assign those. And the 2p orbital that is alone in the sigma symmetric category is the z. Remember that the z, the 2pz, is always the p orbital that is in a category separate, alone, not with the other 2p orbitals. Now, since we're asked about which ones can combine, we then need to check our energies and our relative symmetries. While we have 2 different 2p orbitals in the pi symmetric category, one is an x and one is a y, so they do not combine with each other. So they will make pi symmetric non-bonding molecular orbitals. So our 2px on our beryllium and our 2py on our beryllium have nothing to mix with. Over in the sigma category, we have 4 atomic orbitals. They're all symmetry compatible. If we look at the energies, the 1s on the hydrogen is negative 0.99 Rydberg. The 2s on the beryllium is negative 0.61 Rydberg. Those are definitely close enough to combine. The 2p on the beryllium is plus 0.14 Rydberg. Now that's slightly far away from the 1s on the hydrogen. That's a gap of 1.15 Rydberg, which is a little bit over our cutoff, but still pretty close to it. But it's less than a Rydberg away from the 2s on the beryllium. So we can, in fact, still bundle all 4 of those atomic orbitals together. And so that means that we are going to be combining our 2s on our beryllium and our 2pz on our beryllium and our 1s on our hydrogen and our other 1s on our other hydrogen. All of those are combining. And as it turns out, we will not have any pi symmetric atomic orbitals that are able to combine with anything else. And so the answer to the middle question is none. So there's not a whole lot of point in us sitting down and drawing out our pi symmetric molecular orbitals because they look exactly like the pi symmetric atomic orbitals because there's no combination. It's just atomic orbital renamed to be molecular orbital because the atom became part of a molecule. On the other hand, we had 4 sigma symmetric atomic orbitals that we need to use to build 4 sigma symmetric molecular orbitals. So we will start by deciding what those are going to look like, and we're going to use the same principles to build these that we used to build our molecular orbitals when we were combining orbitals from just 2 atoms. So we start with 4 atomic orbitals. That means we're going to make 4 molecular orbitals. So I'm going to draw my molecule 4 times. And I'll draw it one more time up in the corner here so that we have a place to doodle to show what our atomic orbitals look like on the atom itself. So because beryllium hydride is a symmetrical molecule, because it is nonpolar, we've got the beryllium in the middle and 1 hydrogen on either side. The shape of every single molecular orbital that we draw here is going to have to be symmetric as well. That doesn't mean that the phases will have to be symmetric, but the actual shapes of the lobes do. So we cannot make, for example, a molecular orbital that looks like that. That's not okay. So my principle for building molecular orbitals when I'm combining more than 2 atomic orbitals is I always try and come up with the lowest energy combination for the lowest energy molecular orbital, and then I try to figure out how I can make my atomic orbitals combine with the most possible nodes, and that'll be my highest energy, and then I fill in the middle. So what have we got to work with? Well, on our beryllium, we have a 2s, and we have a 2pz. Those, of course, are both centered on the beryllium atom. And on our hydrogen, we have a 1s, and on our hydrogen over here, we have a 1s. So if I wanted to take a selection of those atomic orbitals and combine them to make a molecular orbital that had as few nodes as possible, I would grab the 2s on my beryllium and the 1s on my hydrogen and the 1s on my other hydrogen, and you can see that's a symmetric distribution. Now when those all combine in phase, there's going to be constructive overlap, and so what we're going to wind up getting is something that looks overall like this. And that is my 1 sigma. And unfortunately, I can't really see the beryllium hydride underneath it anymore, but you know it's there. And that molecular orbital has no visible nodes in it. So that's my lowest energy one. So if I want to make the highest energy combination that I possibly can using those atomic orbitals of beryllium hydride, I'm probably going to start with the 2pz rather than the 2s because it has an extra node and more nodes means higher energy. And then I'm going to combine it out of phase with the 1s orbitals on each hydrogen. So if I have my 2pz drawn like this, then in order to maximize my number of nodes, I would be pulling in the 1s on hydrogen out of phase to the lobe on the 2p that it's adjacent to, and the 1s on the other hydrogen, again, out of phase. And so this then gives me a molecular orbital that has 1, 2, 3 nodes. And that's going to be my 4 sigma because it's the highest of the set of 4. And if I look at that, that should look very much anti-bonding to you. So now that I know that my 1 sigma has no nodes, and I should have a 2 sigma and a 3 sigma, and my 4 sigma star has 3 nodes, then logically my 2 sigma should have 1 node, and my 3 sigma should have 2 nodes, because as we add nodes, we increase the energy. So what should 2 sigma look like? Well, it has 1 node, and the molecular orbital has to be symmetrical in shape, so that means the 1 node has to go down the middle, which pretty much means we're going to be starting with our 2pz atomic orbital on the beryllium, because that's how to introduce that node, and then we're going to be combining it in phase with the 1s orbitals on the hydrogen. And that's going to give us something that looks like this. So we took the 1s and combined it with 2pz in phase and combined that with the 1s on the other hydrogen. And that gave us our 2 sigma molecular orbital with 1 node. And if I look at that molecular orbital, it should look bonding, just like the bottom one should look bonding, because both of those molecular orbitals have a significant amount of electron density along these beryllium hydrogen lines. Then my last molecular orbital of the set that I need to build is my 3 sigma. I need 2 nodes. They have to be symmetrically distributed because I have to maintain the symmetry of the molecule. So I can't have one going through the beryllium and then one off to the side. That doesn't work. So I need to have them equally spaced on either side of the beryllium. Since the only orbitals I have to work with on the hydrogen are 1s, can't have the node going through the hydrogen, so it must therefore go through the beryllium hydrogen bond. And then the way to pick atomic orbitals that work with those nodes would be to have the 2s on the beryllium combining out of phase with the 1s on the hydrogen and the 1s on the other hydrogen. That should also look anti-bonding because of that node right up and down through the beryllium hydrogen bond. And so using that approach, we are able to build all 4 of our sigma symmetric molecular orbitals, predict what they look like, and as we'll see shortly, we are exactly right about what they look like. To rank them in energy, in terms of our diagram, anytime you bring together a bunch of atomic orbitals, the very lowest energy one in the set is always going to have lower energy than all of the atomic orbitals that were used to make it. The very highest one is going to have higher energy than all of the atomic orbitals that were used to make it. And the ones in the middle are kind of in the middle. So now that we've developed the shape of our molecular orbitals, we know what they look like. We've figured out which atomic orbitals did and didn't combine with each other. We're ready to build the energy level diagram. So remember, we have a 2px on the beryllium and a 2py on the beryllium that didn't mix with anything. And so they will have energies equal to the atomic orbitals that they came from. And they are both pi symmetric. On the sigma symmetric end of things, we took the 1s on hydrogen times 2 plus the 2s on beryllium plus the 2pz on beryllium, and we used all of those to make 4 sigma symmetric molecular orbitals. So here we have our sigma, our 2pz, and then we had this guy over here, and the forward and backward one. This is the 2s. There's my hydrogen, and there's my hydrogen. So we've already located those two on our diagram. Now we need to take our 4 sigma symmetric atomic orbitals. We combine them to make a set of sigma symmetric molecular orbitals. As I mentioned, the lowest energy, that 1 sigma, going to be lower in energy than everything that combined to make it. The highest energy, that 4 sigma star, it's going to be higher in energy than everything that combined to make it. What about the 2 in the middle? Well, let's think of them relative to the pi molecular orbitals that we put on our diagram already. Those 2 pi molecular orbitals are each just an atomic orbital. So they are both non-bonding. And since there's only 1 energy level, we'll write the number 1 in front as well. Normally, for most molecules, you're going to tend to have your sigma bonding MOs, and then your pi bonding MOs, and then your non-bondings, and then your pi stars, and then your sigma stars, when you're talking about combinations from the same energy levels of atomic orbitals. In this case, everything's coming from the 2p on beryllium, at least a little bit. So if my 1 pi non-bondings are here, if my energy of my 2p's on the berylliums is there, then it makes sense that the 3 sigma star would be a bit higher in energy than that. The anti-bonding MO oftentimes is going to be higher in energy than the bonding or the non-bonding. Similarly, it would make sense that the bonding MO, the 2 sigma, would be lower in energy than those pi non-bonding molecular orbitals, that it's lower in energy than the atomic orbitals that made it, certainly than the average of the 4 atomic orbitals that made it. Similarly, 3 sigma star antibonding, its energy should be on average higher than the atomic orbitals which made it. So this is a reasonably good guesstimate as to where the energy levels ought to fall. From there, I check if I've numbered all my molecular orbitals. I have. Have I labeled them all bonding, non-bonding, or antibonding? I have. Have I filled in my electrons? No, I have not. I should do that. So I have 4 valence electrons to fill into my valence molecular orbital diagram. And this gives me a very nice molecular orbital diagram for beryllium hydride minus the tie lines. If I want to fill in the tie lines, each of these sigma symmetric molecular orbitals came from the 2s on beryllium and the 1s on hydrogen and the 2p on beryllium. And you can see that those tie lines start getting really cluttered really fast. Also note that because we don't have a third side of our diagram, we have grouped both hydrogen atoms together on the one side. When we start drawing molecular orbital diagrams for even bigger molecules that have more than 2 elements involved, at that point, we're probably mostly going to give up on showing our atomic orbitals on the sides. And so this is the pretty version of the diagram. It has almost everything in place. I just need to add the little stars to show anti-bonding. But again, you can see we have our atomic orbitals, we have our molecular orbitals, we have tie lines looking much prettier than the ones I drew on the previous page because the computer does that much better. We have pictures of all of our molecular orbitals, and they show that our predictions for